Hello, everyone. It is my privilege to be here today with the renowned Dr. Charles Doarn. Today's keynote is brought to you by BeyondSpace in partnership with the American Center in Moscow. BeyondSpace is a 5-month virtual incubator and exchange program for students and early career professionals who are interested in developing new ideas for the space industry. Over the course of the program, participants work in teams to turn a space related idea into a viable concept, learning from industry experts along the way. Today's keynote is open to the public because we believe great ideas should reach as many people as possible. Whether you're a Beyond Space participant or part of the AMC audience, we are thrilled to have you here. And it is, again, my incredible pleasure and privilege to introduce you to Dr. Charles Doarn, who serves as so many titles here that it's like I need to make sure I get them all right. He is the Chief Operating Officer of SolaMed Solutions and an Emeritus Professor at the University of Cincinnati College of Medicine. He's also served as the inaugural Director of UC's Armstrong Institute for Space Technology and Research. And for more than 3 decades, he advised NASA's Chief Health and Medical Officer on aerospace medicine and telemedicine, and co-authored the Federal Telehealth Working Group. He's an honorary NASA Flight Surgeon and has been recognized with the Astronaut's Silver Snoopy Award, which, if you're not familiar, is the highest honor NASA can bestow, and NASA's Exceptional Public Service Medal. Now, this is what's incredible. For several decades, he has served as editor-in-chief of the Telemedicine and eHealth Journal and has authored and edited an extensive body of work in telehealth. You could call him probably the father of telehealth. Dr. Doarn, we thank you so very much for being with us today. The floor is yours, good sir.
Thank you, Janet. That always sounds like an obituary when somebody reads that. I'm glad to be here today, and as Janet commented, I am the Chief Operating Officer of SolaMed Solutions. I have been in this field of space medicine, telemedicine, and so forth since 1990. So it's been quite a while. So I'm looking forward to having a brief conversation with you all. I'm going to show you a PowerPoint presentation with some really cool slides. And then we'll focus on some Q&A at the very end. So anyway, this picture was taken from the Artemis crew earlier this week. This is the Earth rising above the dark side of the moon. And that actually is sort of a replicate of a paper, or excuse me, a photograph that was taken in 1968 on Christmas Eve, actually, in Apollo 8. And so over the last number of decades, 70 years actually, we have been collectively around the world working on space exploration. And so what I wanted to show you, this is just the beginning slide. This actually is a launch pad last week. A friend of ours took that picture, and it kind of highlights the rocket on the launch pad at the Kennedy Space Center. So my comments today are my own comments. They're not necessarily, certainly not U.S. government policy or comments, and they're not the University of Cincinnati's, because I am still an Emeritus Professor. But this kind of highlights some of the activities I've been involved in over the last 30, 35 years or so. So from a historical context, what I wanted to do is sort of build up, how do we get to this point? So if you think about space exploration, in 1915, there was a National Advisory Committee of Aeronautics, which was in the United States, and is really focused on aviation. And at that time, it was actually in the early part of the 20th century when the Wright brothers perfected flight. That was the 3 parts pitch, roll, and yaw for an airplane. And they began to look at how could we use airplanes to deliver mail. No one really thought about aviation as a way of getting from point A to point B. And then somebody said, well, you can drop things from airplanes, and that would include, obviously, bombs for World War I. Well, then they started thinking, well, if we have pilots in these airplanes, are they affected by going up higher in the atmosphere above 10,000 feet? And so the School of Aviation Medicine was established in 1918. Then World War II came. We had the Germans developing rockets with Wernher von Braun. We had the Operation Paperclip, where almost 1,600 scientists moved to the United States or were brought to the United States. The remaining went on to the Soviet Union. The Cold War began, and then after a few events in the former Soviet Union, Sputnik, and the launch of Laika, the dog, which we'll talk about in a minute, the United States established NASA, and NACA employees all became part of that organization. And then also they developed DARPA, which is a Defense Advanced Research Project Agency. And these are just a couple of citations. And you notice on each of the slides, I put down at the bottom either a reference or a website where additional information can be found. This actually is a photograph of the actual law that President Eisenhower signed in 1958, creating the agency. And here are the first individuals with the Space Task Group. The Space Task Group was the organization of individuals that actually were developing early spacecraft, the Mercury program, for instance, in the late 50s. They all became part of NASA, and that was actually out of a site in Virginia. So at the time, when we talk about humans being part of a ballistic missile, if human will put somebody on top of a ballistic missile and send them off somewhere, there's danger, obviously, in that. There was a distrust of the German scientists. In fact, President Eisenhower was very concerned about Wernher von Braun and some of the activities that had been done during World War II. And so there was a lot of political machinations at that time. There was debate whether humans could actually survive. There was debate of whether this was a waste of money. And so there was some concern about that. But the large part of bioastronautics was really with the United States Air Force, which was only formed in 1948-49 time period after the World War II. And one of the individuals that came from Germany was Hubertus Strughold, who turned out to be a physician. Well, he was a physician trained in Cleveland at the Cleveland Clinic back in the 20s, but was a Nazi scientist. And so he was discredited, but he's actually the person who came up with the term space medicine. The question at the time, of course, was whether humans could actually survive in space. So there were a lot of animal studies done. There was competition with the Soviet Union and to see who could get into space first. Now, some interesting things many of you may or may not know. This is President John F. Kennedy on the right, talking to Nikita Khrushchev in 1962 about a possibility of a joint mission to the moon. This was something that the Kennedy administration had actually talked with the Soviet counterparts about doing this, but then Kennedy was assassinated and Johnson didn't want to work that closely with the Russians. And so we went on, as the United States went on to the moon, and then the Soviet Union went on its different pathway. There was always a perceived threat. There was always this contest of who was better at innovation and so on. And so it really built up this political directive to create an opportunity for, the human exploration of space. So in 1961, at a joint session of Congress, President Kennedy made this speech. You can look these up on the websites below. It's a very powerful speech. But I want to underline the entire talk with this concept that, we do things because they are hard, right? They're not. I mean, if it was easy, everybody would do it. This is something that has always been the case in anything we ever do, and it's not just an American concept. I mean, this is actually a concept around the world that if we set our minds to something, we can really achieve a lot. And so the idea was to get a man to the moon and return him safely by the end of the decade, and that was really the driving force. The amount of money put into NASA during the 1960s was 5% of the federal budget. Which was an enormous amount of money at that time. Today, it's more It's less than 1%. And so NASA always struggles for money, just like all the other agencies and departments within the US government. So how did we evolve into this exploration paradigm? Well, Project Mercury, I mentioned the folks at Langley, this Space Task Group. Eisenhower made a directive, all of the incoming astronauts would be test pilots, military pilots from either World War II or the Korean War. And they were selected using United States Air Force selection standards. They were working out of the Manned Spacecraft Center, which is now called the Johnson Space Center in Houston, Texas. And all the evaluations and discussion about whether the crew could actually survive or be, even be selected were done at Wright-Patterson Air Force Base, which is here in Ohio, not that far from where I live, and the Lovelace Foundation, which is in Albuquerque. The mission had limited capabilities to conduct research. So really, the goal of the Mercury program was to build up to the Gemini program, to build up to the Apollo program to get a man on the moon. It wasn't about, let's do a lot of life sciences work. It wasn't a lot of research on whether humans could survive, other than basic tests. So in order to do this, it was an aggressive timeline. As I pointed out, Kennedy made a comment that his speech, that we needed to do this before the end of the decade. So how do you send people into space when it's never been done before? Even back with Gagarin back in the early 60s from the Soviet Union, was you have crew, you have the selection of the crew, you have to observe the crew, what they're doing, you have to track where they are, and that's the map up on the right-hand corner. And the United States had tracking systems all over the world, so you could basically track people, except over the zone of exclusion, which is right between Diego Garcia and Australia, in the Indian Ocean. That's the large part just directly south of India. And then you had to recover them. And then if you were not the right person for the mission, so I'll use an example. Chuck Yeager was riding a horse and fell off a horse and broke a rib, but he did not tell his flight surgeon that he had hurt his rib, so therefore he could not break the sound barrier. So if an astronaut tells his flight surgeon during this time period that, hey, doc, I got this headache, they could take him off the flight, and the next person would be up. Today, we actually have a much better evaluation system to look at astronaut healthcare and determine whether somebody can actually have whatever is going on with them fixed. In this case, one case, for instance, in Apollo 12, one of the astronauts he flew to the moon, but earlier in his career, he wasn't ready to fly because he had a problem with hearing, which turned out to be Meniere's disease. And they didn't, today that would not preclude you from flight. So the point here is that in order to build something like this, we had to develop, systems that had not existed. And one of the interesting things is a lot of engineers often will say, and I remember talking to Dr. Arnold Barrère, who's a famous Soviet physician. He told me that he and Dr. Korolev was the designer of the original Russian Soviet rockets in the late 1950s. He said, Dr. Barrère said, the cosmonaut needs to sit in the rocket in a certain way so the XYZ vectors don't kill him. And Dr. Korolev says, I must build a rocket. That was his idea. He built a rocket, but not necessarily care about the crew. And so you have this dynamic between engineers and physicians, which still exists today in human factors and human systems integration. So that was an interesting point. Now, on the US side, one of the engineers said the astronauts do not need a window. You can see the window where right above Alan Shepard, where the hatch is. There was a window there so they could look out and see things. But in the late 1950s and early 60s, the design did not include a window. The window was way up above at the top of the cone of the spacecraft. And the engineer's like, well, you can't see anything from space. What's the astronaut going to do? So during one of the flights of the Mercury program, the astronauts saw a train locomotive entering a tunnel in China. And they said, there's no way. So he said, well, check the train schedule. And they checked the train schedule. And sure enough, he could see the train. And so they realized you could see things on the Earth from space, which then obviously developed a whole bunch of spy satellites and our ability to look at what's going on the Earth, whether it's in the ocean or whether it's in the mountain ranges or wherever it might be. So from a system design perspective, I mentioned it's an engineering centric approach. Now, because we pushed to go to the moon, our missions were shorter in duration. And there is a difference between long duration and short duration. You might say the current Artemis mission is a long duration mission because it's more than 4 or 5 days. It's actually going to be 10 days with a landing in the ocean tomorrow night. But the United States focused on shorter durations, and the Russians, the Soviet Union, focused on long duration, which basically changed the operational tempo, right? So in the United States timelines, you would have a very detailed list of what to be done during that day. So for instance, from 8 to 10 is a particular research project, and from 10 to 11 is personal hygiene and eating, and then, so on. On the Russian side, it was very focused on these are the things that need to get done today. And the way in which the cosmonauts were paid, like their annual salary, was different than what the American astronauts. So that timeline and that operational tempo changed the dynamics of what could be done in a timely manner. Now, there have been many, many biomedical results reported from the Mercury, the Gemini program. There were a lot more Gemini experiments that Dr. Charles Berry worked on. And in fact, from a short story perspective, he was presenting his work in Prague there's a castle there in 1968 and 1969 time period. And the Soviet scientists were there, and they were kind of stunned that he was so open about the results that he was reporting. So this comes from two different sources, both Dr. Berry and Dr. Sam Poole, who both have since passed away. But they both told me the same story, that basically that Dr. Berry went back to his room, and about an hour after he was in his room, there was a knock at the door with two men in business suits to say, would you like to come to this meeting down in the bottom of this castle? So he went down to this room, and before he went in the room, there was a Soviet soldier standing there. And inside the room were all these Soviet scientists, sharing vodka and drinking, smoking cigarettes and so forth. And Dr. Berry went in and they said, we'd like you to come to Moscow and teach us about space medicine. And he was like, forever? No, he goes, no, just for a couple of lectures. So he went back to his office and didn't say anything to anybody. He didn't tell his wife. He didn't tell any of his colleagues. And about 2 days later, when he returned, the FBI came to his office and said, Dr. Berry, we'd like to talk to you about your recent visit and meetings in Prague. He goes, well, what about him? He goes, well, we understand you met with some Soviet scientists. And they're like, how would they know that? So it turns out that they approached the Nixon administration about collaborating in creating a joint working group. And that joint working group, which I'll talk about in a few minutes, established the foundation of what we do today on the International Space Station, where we collaborate with multiple countries on standards and so forth. So from operational capabilities, the Gemini and Apollo missions began to focus on docking, returning, landing, and making sure the crew could do the tasks of getting on the moon and walking around and doing the research that they were supposed to do. Now, with all spacecraft, you have, or space systems or launch systems, there's a possibility of a disaster. The Apollo 1 fire, which is a picture right under the words lunar landing, actually killed the 3 astronauts in 1968. And then we had landing challenges in Apollo 11, where they were running low on fuel, and Neil Armstrong was able to land without, hitting a rock and causing the spacecraft to flip over. And we know Apollo 13 had a mishap with a the side panel blowing off and having that not landing on the moon, but going around the moon and coming back. And there's a famous movie about that. We also have the Challenger and Soyuz 11 and the Columbia accident. So there's always been the fear of a mishap. And so we learn from those, we create opportunities, and we have challenges in front of us. So how do we address that? And I think that those lessons have to be shared with the commercial space programs as well. We've obviously brought many moon rocks back. Some of those moon rocks have been around the world on tour. They're on loan to different places, and there's actually a large collection at the NASA Johnson Space Center. Now, some of the other issues that were learned about crew health. Now, this is a picture superimposed. It's not the astronaut that had the issue, but this actual picture is Buzz Aldrin, and you can see in the face shield of Buzz's helmet, that's Neil Armstrong taking the photograph. But that EKG is actually from Apollo 14. One of the crew members had an issue with cardiac arrhythmia, and that was all done through telemedicine because, as you know, there's no wire communication between here and the moon, so you have to be able to do that wirelessly. Okay, so we take the next giant leap, right? So that's Artemis. And so the last 5 or 6 slides I want to talk to you about is about Artemis. Artemis is the twin of Apollo. Artemis 1 was launched, I think, 3 years ago as a test flight of the rocket system. If you recall, in the Apollo program, they basically put the astronauts in the Apollo spacecraft and launched them. They didn't do a test flight of the rocket fully assembled. This rocket, if you saw the launch, was spectacular. It went off flawlessly. You have a crew of 3 men and 1 woman, a person of color, and you have a Canadian, so it's not all an American crew. And so this crew goes on to go to the moon. They're still on that journey, and they'll be back here tomorrow night. But it's a mission of firsts. It's the farthest point for any human to ever travel beyond Earth, 4,000 and some miles beyond the moon. The first woman, the first African American, and the first Canadian, as I mentioned. The mission objectives were clear, multiple objectives, if you will, were to test the spacecraft itself, test the systems, and then actually do reconnaissance of the moon for landing sites for Artemis 3, and to begin to do more studies of the moon. And there was 10,000 or maybe even more pictures than that taken of the moon. There's international participation. You obviously have Canadian, you have the European Space Agency participating, you have other nations that are bringing concepts and ideas forward. And of course, there are challenges. One of the challenges, which I'm sure everyone knows, is the toilet doesn't work right or hasn't been working right. So there's a backup system for that. Crew selection is different today than it was in the 1960s. In the 1960s, it was all men. On the Soviet side, there was one woman, Valentina. And after that, you started seeing more women, and they weren't always military. They began to become scientists, researchers. In fact, one of our members of our SolaMed team actually was a backup astronaut for a mission, Alex Dunlap. And so not a career astronaut, but more of a MD, actually both a medical doctor and a veterinarian. And so you have individuals who have a tremendous background that provide unique experiences. Let me just turn my phone off. To bring to the table. So in other words, it's not just the fighter pilot that's the astronaut, it's the average citizen. And both the Soviet Union, Russia, and the United States, and now China have launched, I think the number is almost 700 people into space. And now we have commercial companies sending people into space. But the biggest concern that we have, at least from my experience or my interest, is crew health and performance. Now, the Artemis Accords, the picture on the right, over 60 countries have now signed on to that. And it's really about how do we use space, the peaceful purposes of space, and how do we make sure that we do things in the correct way for protecting the moon, protecting the upper atmosphere, and so on. So this is the mission patch. This is a crew you can see in front of the spacecraft, and this is actually the spacecraft on the way to the moon. So the Artemis mission, as you can see, we're on the blue line now. The blue line is coming back towards number 13. That'll occur sometime tomorrow. We'll jettison the back part of the spacecraft, and the capsule will then land somewhere in the Pacific Ocean off the coast of San Diego. I'm not sure the exact location, but you can see the mission. You basically went around the Earth twice and then jettisoned off to the moon. They were on the dark side of the moon at the farthest point and took a lot of really cool photographs of the dark side of the moon. And then now they're on their way back. So this is just a picture of the crew on launch day. You can see all the systems that were designed. There's not a picture of the screen. These pictures all come from NASA, but the crew members are in their backs. There is a flight rule for astronauts being on their back for more than, I think it's 4 hours. So if they would have had a mission delay of several hours because of weather and they were in there for more than 4 hours, they could scrub the mission if they had to. But these are all self-sustaining crew suits where they all have their own sources of oxygen. Doesn't look like there's a lot of room in there, but if you see the next picture, we have the crew with the to the left. All the suits and so forth are stowed away so they can go about doing their work. And there's an interesting story about this little thing in the lower right. I guess it's off of Christina Koch's hand. She's actually holding a design. A young child was given the opportunity. Well, many children from around the world were given an opportunity to create this stuffed animal that would actually tell the crew when they got to zero gravity. And so that little thing's been floating around. I was going to include a photograph of Nutella. If you all knew what Nutella is, there was a nice picture of Nutella flying around earlier in the mission during a mealtime. Now, the reason why is I wanted to show you this picture. You can see when female astronauts fly in space, they don't normally put their hair in a ponytail or somehow keep it up. So you can see Christina's hair is all over. But what I thought was really cool is right below her is the first aid kit. And you can see the Red Cross. And why is this important? Well, we hope that they never have to use those kits. The kit on this particular spacecraft is much smaller than the one, the medical care capability on the space station. That's a very much larger package. But you have this opportunity for the crew to interact with the ground controllers through a telemedicine link, private telemedicine link, to talk with the flight surgeons and or specialists at the Johnson Space Center, or if it's the International Space Station, they could talk with the Canadian Space Agency, or they could talk to Roscosmos at Institute of Biomedical Problems in Moscow, or wherever the crew is, because there's a downlink capability. I think the challenge for us as we move forward, whereas the communication between the Earth and the moon is delayed by seconds, there is a deep space network, is that when we do end up going on a human mission to Mars, the delay in communication increases significantly to up to 22 minutes one way. And if you're on the surface of Mars, as an example, and you have a problem, I always see people say, you get to the surface of Mars and you step off the platform onto the moon and you grab your chest and you say, Houston, I have a problem. The 22 minutes later, Houston says, what kind of problem is it? And 22 minutes later, you answer. So already 45 minutes, 45 minutes have passed, and now it might be too late. So we start thinking about how do we now begin to create opportunities for smart medical systems and artificial intelligence and so forth. So some of the quick things to talk about. These pictures on the right are from the Space Shuttle or the Space Station program. All astronauts have to do countermeasures. they have to do exercise on a treadmill or a bicycle ergometer, or do resistive exercise devices, because every system of the body here on the left is affected by space. So the life support systems and the atmospheres all have to be controlled and made comfortable for the astronaut. But you also have to potentially produce food. Now, on the mission to the moon, they took everything with them. But on the space station, they were actually, some of the crew's been up there for over a year. And I remember talking to Dr. Polyakov about his mission of 440 some days, and how they did all the exercise they could. He told me he was always in argument with the other two cosmonauts because they weren't doing their exercise. And so when the mission was finished and they came back, he could walk. The other two had to be carried off of the spacecraft. So it's a big issue. You have to be in sync with your crew members, and you have to be in sync with your flight surgeons. Waste management. If you think about waste management, how do you get rid of certainly personal hygiene materials, both urine and fecal material, and how do you get all that out into the get it out of the spacecraft? And then the medical care is preventative, intervention, and then occupational injuries. And there's been several occupational injuries occur. People have gotten they've inhaled, like there was a fire on the Mir a number of years ago. There have been odors that when the flight surgeons get in the capsule to get the astronaut or cosmonaut out, they smell some really bad things, but the astronauts don't smell it. The people in the spacecraft, they don't smell those smells. Some basic human functions, obviously we've heard about the toilet. This is the space shuttle toilet. I have a picture of a newer toilet, but the toilet itself was almost $1.5 million to develop. So it has to work flawlessly, because if you're on a mission with a whole bunch of crew members, you've got to be able to go to the bathroom in private. Sleeping, we heard that Christina was sleeping upside down like a bat. All astronauts can sleep. You can see in the right-hand corner 2 astronauts on the shuttle sleeping, in different angles. There's mealtime in the middle, where the crew's eating together, and there's you have astronaut running on the treadmill on the Mir space station. So the idea is these basic human functions have to continue on. You have psychological impact. You have distance farther and farther away from where you are or where your family is. There's also environmental concerns here on this is the pictures from the Mir. Where do we find stuff? And I remember one of the astronauts back in the 1998, 1999 period said when she got on Mir, she was looking for a particular device that the previous astronaut, American astronaut, had put in this storage area, and because you can't leave stuff floating around, so you have to put stuff where you can find it. I put the word socks in here. There's a video out there of an astronaut on the International Space Station taking his socks off, and when he takes his socks off, there's all this dust that flies around, and so you could inhale that as well, dead skin or whatever. The noise levels for machines, like the refrigerators, the different humming noises and so forth. And a lot of the crew members actually wear hearing protection. It depends on what's going on and what module they're in, at least on the International Space Station. The picture in the middle here, where you've got one Skylab astronaut holding the other astronaut with his finger, that's Skylab. But that had an enormous amount of space to do research. And in the far right is the Spectre module, which was damaged by a collision, which immediately caused a depressurization of the spacecraft. And the crew had to abandon that along with the U.S. astronaut who was living on Mir at the time, his personal belongings. Okay, so you also have physiological aspects, bone, muscle, and mineral changes. The gravity and acceleration induced changes to the cardiovascular system, fluid and electrolyte system. Everyone gets space motion sickness. I've known several astronauts who don't necessarily get that sick on an airplane, but they cannot actually go on a roller coaster, or they get sick when they do acrobatic flying. You have changes in the immunology system and the blood system, neurovestibular reactions. Some people react differently than others. You have issues with the GI and infectious disease can be there as well, and radiation effects. And all this is based on the last 70 plus years of research conducted by NASA and the Russian and Soviet Union. Some more recent from the Chinese taikonaut space program. The taikonauts have been flying on their space station. So we have a growing body of knowledge, which begs the question, how much research needs to be done, or can we depend on that research that's already been done to actually fly the average person on a commercial spacecraft? Do we need to look at research from that standpoint? One of the other challenges, as I mentioned earlier, is these two pictures are the same, but I use them to reiterate there's limited volume for medical care capabilities on the Orion spacecraft, on the Soyuz, on the shuttle. We don't use the shuttle anymore, but there's a very large capability on the space station. But the most important part of this is that you actually have an ability to return to the Earth within 24 hours. And we saw that back in January, where SpaceX Crew 11 came back because of a medical emergency or medical issue. It wasn't necessarily an emergency. But when you're on the way to Mars or on the way to the moon, you can't just turn around. You have to go, like we saw on Apollo 13, you had to fly all the way around the moon and come back. The medical support, all phases of flight, you have in-flight, pre-flight, in-flight, and post-flight. So when you become an astronaut, a cosmonaut, or taikonaut, or whatever we're going to call other astronauts from other parts of the world, those space flight participants actually have to have a medical care review before they go into space, and then maybe track them afterwards. And we track our astronauts for sure. And the other thing is delay in communications. I mentioned that a few minutes ago. And then the research capabilities. What kind of research can be done on a short duration mission? If you look at a small mission, say on Blue Origin, where people fly into space, they're up there for 10 minutes. They're not going to be able to do a lot of research. But we do know when you're up in space for days, weeks, months at a time, you can actually do quite a lot of research. You have the facilities. I mentioned the toilet not working. I know go back a slide. I remember on STS-49, which is Space Lab J, it was a Japanese mission on the space shuttle. One of the astronauts wanted to bring in a tablet that allowed them to actually, it was a tablet they would take if they had an upset stomach. We might take Tums or Rolaids or Pepto-Bismol, or there are other, things off, over the counter. But this particular medicine was vegetable-based, and when you open the package, it had a very strong smell of carbon disulfide. And the carbon disulfide would actually interact with the lithium hydroxide canisters on the shuttle, which basically would make them inert and not work. And the lithium hydroxide canisters are the ones that scrub out CO2. So you have to be very careful about how you design things and what you can and can't take onto a spacecraft. Right. So that's when we talk about facilities. That's just yet another little story. Ethics, we talk about SolaMed is doing a series of roundtables on bioethics and who should fly in space and what are the criteria and so forth. And that'll actually be more definitive towards the end of the summer with reports and manuscripts. But we also look at training. And of course, I mentioned mishaps and being prepared to do that. To be prepared to address a mishap. NASA's healthcare models. This is a slide I got from one of our colleagues. Everyone who flies in space, the longer they're there, the more they adapt. We have pathophysiology. If you're in space for over a year or maybe 3 years, if you're on the way to Mars, your body's going to change. And so we are able to reduce radiation exposure and bone and muscle loss, by doing other kinds of countermeasures, whether it's taking medication for radiation exposure, design of the spacecraft, doing exercise, whatever it might be. You also have return to gravity. So we've seen many astronauts, cosmonauts have issues when they get back to Earth. And like SANS, as an example, mostly men or male astronauts are affected by this, and female is a problem with their eyes. So you have, and that in and of itself is a whole discussion of why that is. And some smart people at the Johnson Space Center are working on that. But clearly we've seen there are health risks for flying in space. We know that the space flight affects every system of the body. And it's not just the physiology, but it's also the cognitive and the psychological impact. So the brain itself, not brain, the tissue itself, but our ability to interact with one another in isolation. And remember, the farther away you go from the Earth, the farther you are away from everything. And so it's sort of like in the Age of Discovery in the 15th century, you're on a boat in the middle of the Atlantic Ocean trying to find the new world because you're on a mission with Columbus and the Portuguese and Spanish kings and queens. So you're trying to find this stuff, and you're out there. You can stop at an island if you find one and get fresh water, and you get fruit and maybe some animals or something. But on a Mars mission, whatever you leave with, if you take this glass of water as an example, you're drinking this glass of water for 3 years. I mean, there's more than one glass, but the point is that you have everything you need. And perhaps when you get there, you might have more materials because it's gone before you have. And the last slide, I just wanted to highlight, this is sort of a NASA slide, Journey to Mars. You can see where the blue is, where we have been the last number of decades. Obviously, the Orion spacecraft is now where it begins to become orange. And we have the ability now, we've already sent robotic systems to Mars. This is many nations have done, well, not many nations, so quite a few nations have done exploration missions out into the solar system, but it's basically been 2 or 3 nations that have been able to do that because the cost of doing this is enormous. I read an article earlier today on the BBC. Why did it take NASA 50 years to go back to the moon? Well, first of all, the expense is enormous, right? And it also comes down to what's the rationale for doing so. If the moon becomes the launching point, I don't mean launching rockets, but the launch pad, if you will, or the point for where we can go and build a telescope and look deeper into space in the dark side of the moon, or we can live there for a period of time before we go to Mars as a sort of a launching point. So it's a huge potential. So with that, this last slide, this is actually an artist's rendition of what a doctor might look like on another planet, where you have a heads-up display. When this picture came out, it's actually on the 3rd edition of Space Physiology and Medicine, a book. I'm actually working on the 5th edition with some colleagues. None of this stuff on these screens were possible. Like these heads-up displays weren't even thought of. I mean, they were thought of in the lab, but they weren't practical. And we see now that they're much more practical. So with that, I'm going to stop the PowerPoint and go to the questions and answers. And I know the questions are here somewhere. Let's see. I have a couple questions here. I was wondering, what would you say that the biggest NASA challenge is right now? Something that the space industry needs to focus on the most right now? Thank you. I think the biggest issue with NASA, or anybody actually, is money, right? The cost of doing what we're doing internationally is of tremendous value, but the amount of money continues to shrink. And actually in the United States, it continues to shrink with each of the last, say, 3 or 4 presidential administrations, whether it's, I mean, there's always a vision and a mission, but I think the biggest challenge is funding, and then the competition with commercial programs. So as an example, if you have commercial programs that are going to deliver capabilities like a lunar rover, as an example. You're depending on those companies to deliver on time, which is always challenging when you're talking about billions of dollars in commercial product development, whether it's a lander, whether it's a rocket. I mean, even the Orion spacecraft and Boeing Starliner took forever to develop. SpaceX has been a little more successful, but you have to be concerned about money. I think that would be my answer. Okay, so let's see, next question. What kind of consequences for the body, maybe psychological, astronauts usually have after returning from spaceflight? Well, I know talking to some flight surgeons, there's often opportunities for them to, opportunities. They cannot drive a car when you've been in space for a long period of time. This happens where the flight surgeon has to be with them until their family, they do, post-flight testing and so forth. And so within, maybe 3, 4, or 5 days after flight, they start to return to normal, and they may not be able to do certain things like take a hot shower by themselves. Or there was one astronaut who was actually on a panel, on a dais, giving a talk, and basically passed out. So you have to watch the crew members, especially if they've been in space for a long duration. If you go up in space for 10 minutes and come back, it's not a big deal. But if you're up like these 4 astronauts, when they come back and they pick them up out of the spacecraft in the ocean on Friday night, early Saturday morning, they are probably not going to be able to just, get out and run a marathon. They're going to be a little wheezy. But again, it depends on how long they've been in space. Here's a question, first aid kit, how does it differ from the usual one on Earth? Biochemistry, physiology change up in space. That's true. One of the things that the kits are designed, there's a standard kit, and sometimes the kits may evolve based on what's on the mission. I remember in the shuttle program, one of the astronauts had to take a tonapen, and although most people don't know who's using the tonapen or who's using a particular medication, as this is privacy, we try to keep everything the astronauts are doing private. But the basic first aid kit is to address certain things. There's certain kind of medication for space motion sickness, pain meds if you get something in your eye. On the space station, there's minor surgical kit. If you got a cut, they would be able to fix that. But major things are different. And I'll use an example. In 1991, when I was working at the Johnson Space Center, we did a series of studies on the KC-135. The KC-135 is an airplane that flies in parabolic flight, right? And so when you get to that top and you start to fall forward, you get about 28 seconds of microgravity. And on that particular flight, we were looking at albuterol inhalers. And I don't have an inhaler, but I'll use this bottle of this glass of water, right? So I have this glass, right? So you can see the glass is, almost full. And so we tested 3 different size bottles of Cepacol, the stuff you spray in your throat if you have a sore throat. One was full, one was half full, one was about a quarter full. And in space, what happens is that the liquid goes up along the side, so you have this bubble in the middle. And so we did that first to test to make sure that was true, and then we did these albuterol inhalers. And so I would take the inhaler that was full, half full, and 1/8 full, and spray it into a separatory funnel, and then we do chemical analysis afterwards to see if the metered dose was in fact true. The problem is with the metered dose, you have your liquid, right? I'm drinking this water, so I'm not going to do this. You have your dipstick here, and when you pump down, it sucks up whatever's in the container. But if you have the container has that bubble, it's not getting a metered dose. So that's the delivery system of a medication. Then you have people who are actually taking medication, whether it's say Tylenol or Advil or something, some ibuprofen or whatever it might be for pain. It might interact differently. And so there's a whole group of people at the Johnson Space Center who are looking at pharmacokinetics and the pharmacology and the way in packaging drugs, the way in delivering the drugs, and how they actually interact with the body while they're in space. Okay, so the next question is, do the training and requirements for female cosmonauts differ from the male cosmonauts, and if so, how? I think all training is basically the same. I mean, depending on what, so if the female astronaut has to be trained differently on the toilet system because it works differently. But I think when you're doing a particular research project, whatever it might be, you're going to get the same training. Now, if you're doing an EVA, the EVA suits are basically the same. The flight suits are slightly different. And I know one of my colleagues, Dr. Sarah Lynn Mark, will be on, I think, may be able to address that a little more. I think that if the cosmonauts are all, in my mind, they're all trained, basically the same, unless it has to do with flight suits, the toilet, and whatever experiments they may be working on. Okay, let's see. We go down here. If classical telemedicine is real-time consultation, breakdown delays in space, so how do we design asynchronous telemedicine protocols? It's more about data and AI or something else entirely. Okay, so when we started doing telemedicine in 1990, well, I started doing telemedicine in 1990. There were the synchronous and asynchronous, and we developed a web-based tool. It was called the Space Bridge to Moscow. It was actually after the Space Bridge to Armenia, which was in 1988, where the United States, through the Joint Working Group, was able to develop and address remote healthcare in the Soviet Armenia, and then a train derailment in Ufa, Russia. And that was all done using real-time interaction, right? Because we had two satellites. One was on this side of the world, the other one was on the other side of the world where Russia is. And so you'd have ground terminals. So you beam up to one satellite, down to the ground terminal, up to the next satellite, down to the other, right? And so today we can use this device and talk to anybody in the world in real time with very, very little time delay. And so when we were doing that Space Bridge project, we developed a web-based interface that allowed us to do real-time video conferencing or store and forward, which is asynchronous. And so you basically put material into a web-based tool. And I remember back, it must have been 1998 or 1999, I asked somebody, why can't I have, and this might blow everybody's mind, why can't I have an AI system that I feed into it the x-rays of my patients, and they come back and say, oh yeah, it's 100% tuberculosis, and this is the medication you give them. And I was told in 1998 that was not possible. And so we know today, when we develop smart medical systems, that we're going to be able to have avatars and or robotics that are going to be able to help us deliver healthcare. In fact, one of our flight surgeons, Joe Schmid, at the Johnson Space Center, actually beamed himself as an avatar to the space station. So he was not physically there, but as an avatar. And this was supported, I believe, by Google. And so it's very conceivable within the next several years that we'll be able to do medicine in a much different way. There's still the hard part of medicine, putting a Band-Aid on somebody or doing a surgical intervention. But there's research out there that's changing all that. And I think the same with telemedicine is that there are many different kinds well, there's basically three types. The asynchronous, synchronous, and then you have real-time monitoring. And so it's just adding the tools and the communication link. If you don't have the communication link and you're autonomous, then that means you have to be trained and have a link. And so if you're trained and go look for something, like as an example, you can see behind me, there's a lot of space medicine books, aerospace medicine books and so forth. I can look in that book and find something or find whatever I'm looking for, or I can go to PubMed or Google or the National Library of Medicine or to Scopus or Web of Science, and I can find the answers to things that I couldn't do, say, a generation ago. So I think that will be, I hope that answers the question. It'd certainly be interesting to see. Okay, let's see. Uh, hello, do ordinary medical equipment work the same way in space? Yes and no. When I remember when we were working on developing a surgical care system, you could, and actually there were several flights on that vomit comet plane I told you about, where you have you're doing surgical procedures, and you actually have blood that would, if you cut an artery, it's going to squirt out, right? So in space, the blood becomes like droplets. So you've seen on the in television show or news programs or movies where you might have little bubbles of water floating up, or that some astronauts will put water and then they'll have a bubble and they'll catch it with their mouth, right? So you have the microgravity affects the way the blood works in space. So we had to develop a entrainment system that allowed it would lay over the body, so that if a blood squirted up, it would kind of entrained in the air and it would float away and be collected. So you have to think about the microgravity environment, but electrical power works the same. The ventilators would work the same, although there might be a little difference in the oxygen delivery system if the pressure is different. So it would be challenging for sure. But when they do all the testing and evaluation of products and services that they use on spacecraft, they go through all that testing as well. Are there health benefits to being in space, or is it purely a challenge for the body? Well, there has been some work with the European Space Agency to fly a person. They're actually going to fly. I don't know that he's already flown. He might have already flown. A person with that's missing one of his legs. So he lost his leg, I think, in Afghanistan or Iraq, somewhere. Anyway, so the idea is that you don't need your arms and legs to work. I mean, they even talked about Stephen Hawking going up before he passed. Well, he was never going to go into space, but there was talk about somebody like him going up where he didn't have the ability to use his arms or legs, but he could still be in space and be contributing in some way, right? So the only reason why you need to be able to have your legs is if there's a mishap and you have to get out of the spacecraft. On the space shuttle, you had to carry a 75-pound backpack, which was a parachute, and your breathing system. You had to get off of the space shuttle and run, right? Now at the Kennedy Space Center, each of the launch pads have these long wires that go. There are baskets, and you get out of the spacecraft, you get in the basket, and it basically flies down this hill, and then you immediately go into an MRAD, which is like a tank kind of a facility where you get in there and you're protected if there's like an explosion or something like that. But from a health benefit, I mean, from a psychological perspective, the longer you're away from space, the longer you're away from your family, would have an impact on you. But I think from what we've heard from our astronauts, being able to look out and see the Earth and see the beauty of our blue marble planet, if you will, there's some psychological and some even say religious impact. But I think that might be different for each person. Certainly their body's going to change when they come back. It'll acclimate back to normal, with the exception of the eyes. They have been impacted, but it's not that somebody's going to go blind, but they do have some challenges there. Okay, I think that's the only questions I have.